let's do that so I don't forget. And then just let me fix my windows. I go full screen, everything breaks. Okay. All right, so today we're going to talk about uniform continuity. And if I manage to finish uniform continuity, great, we'll talk about some other hard things. So uniform continuity. And you might look at this and you might be like, okay, this is great. Why is this useful? Because you probably believe that like continuous things are important. Yeah, we need to know something about those. But why do we know something about uniform continuous things? And well, maybe you don't think that yet because I haven't defined it. So here's the idea. The faster that something grows, the smaller the delta you normally have to choose, right? So if you have the same sized epsilon, then if a function is growing very fast somewhere, you probably have to use a very small delta. And if it's growing slow somewhere, you can use a much bigger delta, right? You can always choose a smaller delta, but sort of like the biggest delta which works necessarily becomes smaller as your function grows faster, right? So for a fixed epsilon, the delta that we have to choose basically scales proportional to how quickly the function is growing. The delta that we must choose changes proportionally to how quickly the function is growing. And I'm going to throw that in brackets because we don't actually have a nice way of defining that. But I mean, if you look at the graph of a function, you've got some sort of rough idea about what it means for the, a function to grow. So to how quickly the function is growing. All right, and let me give you an example of that. So let's just compute two limits really, really quickly. They'll actually be continuous, but we'll compute them as limits. And I'm going to use the same function and basically the same epsilon, right? So let's say set epsilon equal to 1, or maybe let's define the function first. We don't want to choose a linear function because linear functions kind of grow at the same speed. That's kind of boring. So let's choose something that actually does grow faster as x becomes bigger, something like x squared. So let f of x be x squared, fix epsilon equal to 1. And then let's, for this epsilon, let's prove that the limits at like 2 and 100 are what they should be. So let's show. So as we approach 2 of x squared is 4. And let's say 10 for this epsilon. So we're not actually going to do the proof in general. All I'm going to do is I'm going to find a delta which works for epsilon equal to 1. And the reason why I'm going to do that is I want to show you that the epsilon, in some sense, the best epsilon that I could choose at 2 is much bigger than the best epsilon I could choose at 10, right? Because 10, the function is growing very, very quickly. So I'm just going to kind of grind out the sort of proofs very, very quickly. So for the limit, it's not even a proof because it's actually for a fixed epsilon, right? So we're going to say, well, x squared minus 4 is x minus 2, x plus 2. You've all done this a million times, right? The x minus 2 is the good thing. That's the thing I want to keep. I want to bound the x plus 2. So let's assume x plus 2 is less than 1 in the usual sense, right? So what does that do? So x minus 2 is going to be less than or equal to 5. Or x plus 2 is less than or equal to 5, right? Let me just double check that. X plus 2, x minus 2 plus 4, x minus 2 plus 4 like that is less than 5, right? Okay, perfect. I guess I could put a strict less than here. So I'm going to take delta to be the min of 1 and epsilon over 5. But in this case, I actually know what epsilon is, right? I said let epsilon be equal to 1. So I guess I kind of did do the proof, but I'm going to, we're working with epsilon equals 1. We've got this epsilon band of width 1. So in this case, epsilon over 5 is 1/5. So the min of that is actually 1/5. So I know exactly what to set delta to be, right? So delta is 1/5. Now I'm going to do the x squared as x approaches 10 even faster, because it's pretty much the same argument. So x squared equals 100. So to do this, we're going to get x squared minus 100. That's equal to x minus 10, x plus 10. Again, so we're going to assume x minus 10 is less than 1. So x plus 10 is bounded by 21. All right, so we're going to take delta to be the min of 1 epsilon over 21. And epsilon is equal to 1, so we're going to take 121. 1 over 21, like that. Okay. And yeah, there might be some sense in which this isn't the biggest delta that we could possibly choose, but it's pretty close, right? I use the same sort of approximation method each time. So if there's any inefficiencies in how I chose delta in the first time or in the second time, they'll basically be the same. And we see that for x equals 10, I have a much smaller delta. Do we need to assume x minus 2 for the first one is x plus 2 right now? I'm not certain what you're saying. So, because, right, I'm trying to bound the x plus 2, right? So in order to do this, we usually have to make an assumption about how near I am to the number that I'm limiting to. Oh, sorry, you're right. That should be x minus 2. Maybe that's what you're saying. Yeah, you're right. I see what you're saying. Yeah. Okay, so we see, and you can imagine, as I choose bigger numbers, I could very easily do this proof as x goes to 25, show that x squared then limits to 625, and do the same sort of proof. And you imagine I get smaller and smaller numbers. And the reason for this was so we can see this graphically, right? So if we plot it, and I don't think that my drawing here is going to be very good. I for whatever reason, can draw much better on a real blackboard than I can on my tablet, but let's give it a shot. All right, so x squared looks something like this. Okay, and let's say that this is, I've really scaled out. This is the number 2, and this is the number 10. Okay, and I'm going to try and draw an epsilon band here. I'm also going to try and use all of my colors. And I'm going to try and make my epsilon bands the same width. That's way too big. What are you doing? Too big. Oh, can I delete this? Yes. Okay. Okay, so this is going to be my epsilon band. And if we find a delta which works, actually, maybe I can use black. So maybe, we found a delta and this delta worked. All right, so this is delta here, like that. So now if I try and draw, what I'm going to try and do is draw the same width of band over at 10. And if I do that, maybe let me not go all the way to the left-hand side, because it's just going to get really, really bad if I do that. All right, I know you're colorblind, but let's try and use the same colors. Right, so it should look something, I think those bands are about the same width, right? I think they look pretty close. And if we try and find a delta which works, obviously we've got a much smaller delta, right? So if you look at the size of these delta bands, you see that the one near 10 is much smaller than the one near 2. And the reason for that is the function is growing, right? So you can imagine if you take this band, this epsilon band of fixed width, and you place it at different parts of the function x squared, then as the function grows faster and faster, this delta band is going to get smaller and smaller. And now the delta band is always possible to find because we know that this function is continuous, but the delta band is continuously getting smaller because the function is growing faster and faster, right? So our choice of delta band shrinks as x squared grows faster. Okay, so here's the idea though of what we want to be able to do. We want to say the width here is 1, yeah. Well, or the width is 2 because the length from like the half of the band is 1, right? But this is just an approximate drawing. The point is that if you chose 2 epsilon bands of the same size, regardless of how wide the band is, if you draw one at 2 and you draw one at 10, the band you get for 10 is smaller than the band you get from 2, right? That's the idea there. So what you want to be able to say is something along the following, like, well, okay, well, choosing epsilon over 21 worked at 10, and I know I can always choose a smaller delta. So maybe if I chose that delta for everything, like what if I'd used the epsilon over 21 when I was doing the limit at 2? Well, that also would have worked, right? Once you know a delta which works, you can always choose a smaller delta. There's no issue with that. So what we'd like to effectively ask is there one delta which actually works for every point? So instead of having the delta change as a function of where I'm doing the limit, can I find a single delta which works for everywhere in the function of the domain? So let me kind of like highlight this using quantifier notation. So when we say that f and let's name f, and let's say D is its domain, right? We don't care what it is. It's just some domain. When we say it's continuous on D, we mean, okay, so I'm going to write out the epsilon delta definition, but I'm going to add something. Because you're continuous on the whole domain, remember, being continuous is normally just defined as being a single point. So if I say you're continuous on your whole domain, it means you're continuous at every point. So what I'm saying is that for every C in D, and for every epsilon greater than 0, there exists a delta greater than 0, such that for every x, I usually put R here. Let me just put for every x in D, because it doesn't matter. No, we're doing continuity, so I don't want the 0 less than. Right? And so here, kind of the only thing that's different than our normal continuity definition is I've included this for every point in the domain. I'm continuous at that point, right? So the positioning of these quantifiers, the fact that this occurs here and this occurs here, these two things say that delta is allowed to depend on C. Right? We're saying right from the very beginning, the very first variable I define is C. And then when I define the existential quantifier after it, that is allowed to depend on any variables that came before it, right? That's the rule with existential quantifiers. Once they pop into existence, they're allowed to depend on any variables that came before it. So in this case, delta can depend on both epsilon. We know that. It's almost always written in terms of epsilon, but also in terms of C, right? Yeah, to some extent. And so now what I want to do is I want to say, is there a delta which works for all the C's? So what I'm going to do is I'm going to take that first thing and I'm going to go boop, and I'm going to start to move it over, and I'm going to plug it basically in and around here. So definition. So a function f from D to R is uniformly continuous on D if for every epsilon greater than 0, there exists a delta greater than 0, such that for every x, and I'm going to keep it as C, usually I would use a y, but for every x and C and D, x minus C less than delta implies f of x minus f of C is less than epsilon. Okay. F maps D to R is continuous on D is the same as saying F is continuous. Right. Yeah. It's continuous on its domain. So I'm saying it's continuous on D. Yeah, exactly. Okay. So here, the difference between being continuous on D and being uniformly continuous on D is precisely the location of this universal quantifier for every C and D. Continuity, if you're just continuous, that quantifier occurs at the beginning. If you're uniformly continuous, then that quantifier occurs next to the X, right? So we're saying whenever X and C are a distance delta apart, we can guarantee that f of X and f of C are epsilon apart. And there's a real sense in which this is a statement about bounding the growth of a function. It's not immediately obvious. You kind of have to think about it for a little bit. But what you're saying is there's some delta, right? If you give me some epsilon, there's some delta such that, yeah, no matter what, if 2 points are this far apart, this delta apart, then f of those points can't be more than epsilon, right? And that doesn't happen with x squared. If you take x squared on the domain 0 to infinity, that function grows so quickly that, yeah, it doesn't matter what epsilon you give me. If I let x be really, really, really big, the function is growing so fast that even 2 points that are this far apart, their function values, right, if I compute f of them, will be really, really spread out, right? Because the function just keeps growing quicker and quicker and quicker. So x squared doesn't satisfy that on 0 to infinity. However, x squared actually does satisfy that if I restrict myself to a domain of finite size, right? So if I restrict myself to, for example, 0 to 10, the interval 0 to 10, x squared will become uniformly continuous. Okay, in some sense, like there is a worst delta, there is a smallest delta, which kind of occurs at the point where it's growing fastest. And then after that, we can just use that small delta for everything else. That's the idea there. Okay, so does everyone get the gist of what uniformly continuous means? Okay. So that again, that placement is very, very important, right? So if f is bounded and continuous, it's guaranteed to be uniformly continuous. No, that's not true. And what could happen is think about the function sine 1 over x. That function begins to oscillate very, very quickly. And so it becomes very difficult to keep it in an epsilon band, even just anywhere near 0, right? So even if you're just kind of like on open 0 to 1, sine 1 over x is changing speed extremely quickly. If you think about derivatives, if you've seen derivatives before and you think about derivatives, think about if you're oscillating infinitely often, you're going very quickly up and then you immediately switch speed and go very quickly down and then switch speed and go very quickly up. And so this inability to bound kind of how quickly your function is changing really inhibits your ability to say something about uniformly continuous. So generally bounded and continuous is not enough. You really need some sort of bound on how quickly the function is allowed to change. Okay, what do you mean finite? Yonje, where did I write finite, or did I say it somewhere? You clarify that and I'll answer Mahmoud's question. So any function that is growing faster and faster cannot be uniformly continuous over an infinite domain. That's not necessarily true. This is just kind of like a first order understanding of what uniformly continuous is. As a general rule, growing faster and faster. Can I come up with a counterexample for this? I want to say like instinctively no, but I suspect if I thought about it long enough, I could come up with an example. Because there's often like, what does it mean to grow too quickly? And there's often a weird threshold, like where you can get away with things, but I'm hesitant to say. I feel like epsilon x might work. Like I feel like epsilon x might be uniformly continuous. I'm not certain. Between 2 and 10. I don't know. I don't remember saying finite. But yeah, if you can like pinpoint exactly what I said. So basically, yeah, let's so my idea here. Yeah, oh yeah, okay, yeah, like a finite domain. So something that doesn't like go off to infinity, right? And we're actually going to prove that. I'm going to prove for you that if you're continuous on a finite domain, on a closed and bounded domain, that you are actually uniformly continuous. And that's going to be the hardest proof we've probably ever done in this class so far. So that is true, and we're going to end up using that a ton. But basically, x squared is not continuous. So here, let me say these. I'm going to leave these as kind of exercises for you. And they're in, I think, both Spivak and my book, but I'm going to, when I actually do examples, I'm going to do different ones. So the function f from, let's just say 0 infinity to r, which takes x to x squared, is not uniformly continuous. Right? But the function g, let's close it off. 10 to r x to x squared is uniformly continuous. Okay, so once again, we really see that the domains are playing an integral part, right? Because x squared can't grow unbounded on the interval 0 to 10, right? It kind of limits in how quickly it's allowed to grow. But x squared on 0 infinity, there's no bound to that, right? That thing can grow as fast as you want. There will be uniformly continuous functions on infinite domains. That's not impossible, okay? If you really want, we could do another exercise. So this function is uniformly continuous. Okay, and again, you can kind of see it in the sense that like the square root of x is actually growing slower over time, right? Like the square root of x kind of starts off very, very sharp if you think about its graph, and then it kind of, you know, it doesn't have a horizontal asymptote, right? It's always growing, but its growth really slows down over time. And that actually allows you to talk about the uniform continuity of the square root of x, right? Stephen, did I answer why x squared was not uniformly continuous for you? I don't know if where you kind of posted that in the chat, but like, so on 0 infinity, it can grow as fast as it wants, right? But on the interval to 0 to 10, it's bounded in how quickly it can grow. So when it can grow as fast as it wants, right? It keeps growing faster and faster and faster over time. The delta bands have to keep getting smaller. There's somehow no smallest delta, which works everywhere. But on 0 to 10, there is a best delta, right? There's one delta, which is the smallest that delta has to be, and then it doesn't need to keep getting smaller because the growth is bounded. Is that good? That's just an intuition, right? Like you still have to prove it, but this is sort of the intuition that you use in order to guide it. Does this function grow really, really quickly, right? Can we choose an arbitrarily? Well, not for x squared, so you can actually try this. So for x squared on 0 infinity, just be like, I'm going to choose epsilon over 1,000,000, right? That's going to be my delta. But the point is that I can actually, if I go really, really far, if I let x be some stupidly big number, epsilon over 1,000,000 is not going to work, right? So, and remember, you also have to prove it, right? You actually have to prove that your delta works. So yeah, keep that in mind. But yeah, it turns out with x squared on 0 infinity, you keep having to choose smaller and smaller things, right? For the first one to not be uniformly continuous because the smallest x minus c can not be defined. Basically, it's that delta keeps getting smaller, right? You can actually, if you do this, try doing this proof here for x squared. Try doing it for a general c, right? Don't do it for 2 and 10 like I did. Do it for a general c, and you'll get a formula for epsilon, for delta in terms of epsilon. And what you'll find is that basically as you let c go off to infinity, delta is going to become 0. But delta can't be 0. Delta has to be positive, right? And so that's basically, again, an intuition thing. You'd still have to prove it, but that's basically an intuition thing, right? So let me give you a couple of examples of how I'd actually prove uniform continuity and prove not uniform continuity. And maybe that'll help influence you as well. So maybe let's say something like, so let's show that this function, f from 0 infinity to r, x to 1 over x is not uniformly continuous. right? And again, our idea here is that we know that 1 over x, even though 0 is not in the domain, we know that 1 over x has this vertical asymptote at 0, right? So it starts to grow arbitrarily quickly. And so what that's going to do for us is break uniform continuity. All right. So let's do this. So when I'm proving not uniformly continuous, right? If I go up, so let me just write it down here. So we want to show, some people will do this by contradiction, which is a totally fine way of doing it. I'm just going to prove it directly though. So we want to show that there exists an epsilon greater than 0, such that for all delta greater than 0, there exists x, and I'm going to call it y now, in 0 infinity, such that x minus y is less than delta, and f of x minus f of y is greater than or equal to epsilon, okay? So let's set epsilon to be 1. It's not going to matter, but let's just set epsilon to be the number 1 and let delta greater than 0 be given. Okay, I'm going to break it into 2 cases. So case 1. Oh, you know what? Maybe let me graph this just so again we kind of have an idea of what's going on. Y, and then let's see if I can graph this. That's not good. All right, so y equals 1 over x. And so the idea is that the function is getting very, very sharp, right, towards 0. It's kind of growing arbitrarily quickly. We've got this epsilon equals 1 band. Now, the idea as a general rule is going to be that I'm going to need to get really close to 0, right? Just kind of using our intuition here, I'm going to have to get close to 0 in order to ensure that the function grows very, very quickly in order to break this. I still don't like this graph. Okay, that one's a little bit better. Okay. All right, so let's give this a shot. So case 1, let's assume that epsilon, or let's assume that delta is big. So if delta is bigger than 1, right? So if delta is bigger than 1, they're giving you a lot of freedom to move around. Yeah, okay, so if delta is bigger than 1, we can just choose 2 points. It's really easy. So if delta is bigger than 1, let x equal 1/10 and y equals 1 over 100, right? So then x minus y is certainly less than delta, right? They're definitely, those 2 numbers are definitely within 1 of each other. And f of x minus f of y is 10 minus 100. That's equal to 90. That's definitely bigger than 1, right? So that's kind of the dumb case. That's, you're allowed to basically move pretty freely. So we're just going to choose 2 numbers which definitely break the epsilon equals 1 band, right? By choosing them really close to 0. Now, the trickier thing happens when delta is not bigger than 1, right? So suppose 0 is less than delta is less than 1. Now, here's the issue. When delta was bigger than 1, basically my argument was I can choose 2 numbers which are arbitrarily close to 0. The trickiness when delta is less than 1 is delta could actually be really, really small. And if delta is really, really small, I have to be very clever about what I choose to be x. Because when I choose y, y has to be within a distance of delta of x, right? So I need to make sure that I choose x close enough to 0 that no matter what 2 points or basically no matter what y I pick, x and y are going to be really far apart. Yeah, true. Technically less than or equal to 1. Then maybe put the equal sign above in case 1. But yeah, you're right. Okay. So does that make sense? Like I have to be, because I can't just basically choose x and y to be as close to 0 as I want, I have to make sure that I choose x such that choosing a clever point y within a distance of delta guarantees that they live far enough apart, right? And so what I'm going to do is I'm going to choose x to actually be delta. and y to be delta over 2. All right, thus, I think this works. So certainly, thus, the absolute value of x minus y, that's equal to delta over 2, which is less than delta. And does this work? So let's check. You might not want to write this down until I've double checked that this works. So we're going to get 1 over delta minus 2 over delta, which is equal to 1. Yeah, okay, I think it works, right? It's equal to 1 over delta, but I know that delta is between 0 and 1, so 1 over delta is now bigger than 1. Right? That's because of this. Because I assumed that delta was less than 1, so 1 over delta will now be bigger than 1, and yeah, I've broken my epsilon band. So I had to like kind of be clever about how I chose, you notice how I had to be clever about how I chose x and y, and I actually had to choose them to depend on delta, but that's fine, right? If we again look at the negation of the definition from very above, the delta was defined before I existentially said x and y had to exist, which means that x and y are allowed to depend on delta. And actually, as a general rule, will depend on delta, right? So what have I shown? I've shown that I can find an epsilon such that no matter what delta you give me, it's possible to find 2 points which are within that distance delta of one another, but their function values are further than 1 apart, right? And again, that entirely works because 1 over x is unbounded near 0. Right? How did I break this? You gave me a really, really small delta, and I said, okay, I'm going to choose x to be really, really close to 0 as well, so that 1 over x is actually really, really big. Right? Does that make sense? It might help if I show you. So what I'm going to do then is say, listen, if we actually take out 0. So if we start the domain strictly away from 0, this function actually becomes uniformly continuous. So let me maybe show you that one as well, and maybe that'll clear some stuff up. Okay, so example. So let's say show that f mapping A infinity to R, x maps to 1 over x, is uniformly continuous as long as A is greater than 0. Continuous for any A greater than 0. Okay. So yeah, let's take A to be like basically I'm just going to prove it for general A, right? So let's do some rough work here, right? Because I'm trying to prove some sort of limit statement. So rough work, we're going to have, what do I want? F of x minus f of y. That's going to be equal to x, 1 over x minus 1 over y. That's going to be equal to the absolute value of x minus y all over x times y. And I can drop the absolute values there, right? Because x and y have to be in A infinity, where A is positive. So x and y are both actually positive. I have to keep the absolute values on x minus y because I don't know which is bigger. But x times y, both of those numbers are positive. I don't need them anymore. So the absolute value of x minus y, that's great. That's the thing which I have control over. That's the thing that I can make less than delta. Now I need to bound x and y. But notice that I can do this. Because x and y are both bigger than A. Right? So this means choose delta to be A squared epsilon. And notice that this does not depend on which points x and y I'm dealing with, right? There's no, that doesn't come in at all, right? I was able to find a delta which works for any epsilon irregardless of what points X and Y, right? So the proof would be our standard sort of proof. I'll actually write this one out because it's our first uniform continuity proof. Let epsilon greater than 0 be given. And set delta to be a squared epsilon. Thus, if x minus y is less than delta, then f of x minus f of y is equal to the absolute value of x minus y over xy is less than or equal to x minus y over a squared is less than a squared epsilon over a squared equals epsilon as required, right? Like that. Yeah, exactly. How do we know x is bigger than a? It's because the domain of the function is a infinity. So we know that no matter what two values of x and y you give me, they have to be in the domain of a. So they have to be in this set, which means they're bigger than a. Yeah. Mm-hmm. Yeah, actually, because notice, yeah, absolutely. So yeah, we could do this with an open. Notice the proof doesn't change at all. X and y are the only changes is that, see here, instead of a greater than or equal to, we would just use a strictly greater than, but that actually doesn't affect the proof anywhere, right? A squared epsilon still totally works. So everywhere where it's kind of a non-strict inequality, I just make a strict inequality, but like epsilon delta is very happy to work with a strict inequality. So we can totally do that as well, yeah. And we can see like this proof doesn't work if a is allowed to be 0 though, right? Because I can't divide by 0. That's sort of the issue here. So the idea, even from like a geometric viewpoint, is if you look at the function, if you make some sort of cutoff here, right? So maybe I say this is a, and I cut it off there. The function grows fastest at a, right? That's like that is where the function has the steepest slope. And because of that, basically what you can do is you can find the delta which works there, and that's going to be a delta which works everywhere, right? Because we know that deltas get smaller as the function grows quicker. So basically I found the place where the function grows quickest, found the delta there, and said, look, this delta works everywhere, right? So that's effectively what actually happened. Okay, and that's why this proof here actually works. Okay, now again, normally when you do a proof, it's going to depend on x or y, right? And you kind of can't avoid that. But in this case, we got a little bit lucky here. 1 over x is a nice function, and we were able to find a delta in terms of epsilon, but not in terms of c, or in this case, y, right? There is no c or y. Normally that's allowed to be in there, but it's not in there here. Okay, are there any questions about that? Does everyone see how c would normally come in? Like how, or y would normally come into the delta? Like if it wasn't 1 over x, say. It's okay? Okay. So we immediately have, I don't know, it's not quite a corollary. I guess it should be, I guess it's more of just a comment. So comment, if f, and there's nothing to prove here, is uniformly continuous, then it's continuous. Right? I don't think I need to explain that one, but I mean, if you want me to, you can. But like the definition of uniform continuity is actually a stronger statement than being continuous, right? The statement of continuity says that you can, for every epsilon, you can find a delta, which depends on your limiting point. Uniformly continuous says, actually, you can find a delta for every epsilon, you can find a delta, but that delta actually doesn't depend on your limiting point. So uniformly continuous is a strictly stronger condition, right? You've removed the fact that delta has to depend on its limiting point and said, no, actually you can find one that just works everywhere, right? It's in some sense, it's a better proof of continuity because you said, listen, once I find this one delta which works, now this delta proves continuity at every single point, right? I don't even have to do anything beyond this. I just immediately get this. If you're not 100% certain about this, I suggest that you try proving it, but you'll find that it just falls apart incredibly quickly. Like you know, what's the analogy here? It's like pulled pork, right? Or you slow cook something. It just, the moment you take a fork to it, it just shreds in front of you because it has no structure to it. It's so immediately true, right? So give it a shot and see if you can actually write it out. If you don't see it, it's fine, but start writing it out and you'll be like, oh yes, this just does what I want. I have a delta which works from uniform continuity and it clearly works for the definition of continuity as well. Okay, now the other thing we're going to need, which I'm going to make you prove on your next assignment, but I actually need it, so. So what do I want to say here? If IN are these closed intervals, AN to BN, I guess I should say N equals 1 to M are closed intervals such that, and this condition I don't actually think is necessary. For all N equals 1 to M minus 1, and F is uniformly continuous on each IN, then F is uniformly continuous on the union. Oh, let's use N. Okay. So this was a really long way of just saying the following fact, which is not probably surprising. So if a function is uniformly continuous on these three intervals and these three intervals all touch, then it's uniformly continuous on the entire interval, right? So being uniformly continuous on each, then it's uniformly continuous on everything. And I'm getting a little bit lazy and writing like UNICTS because I don't want to write uniformly continuous every single time, but hopefully it's clear what that means. Okay, so I'm going to have you prove that in your next assignment. You imagine the proof's not actually terribly difficult. Excuse me. Like basically, you know there's a delta which works on each of them. And if you choose the smallest of them, then that delta will probably work for I1 union I2 union I3, right? How do we know the interval's open? Or how do we know the intervals touch? That's the Bn equals An plus 1 condition. Right? That's saying that the right endpoint of one interval is the left endpoint of the next interval. So they actually, they touch there, right? Here's A1, but this is also oh, sorry, maybe this should be B. Sorry, this is B1 and A2. Oh no, so I had that right. Right? Okay. What if closed interval changed to open? In that case, you'd want to make sure that they overlap. I don't think it actually does make a difference. This should actually hold for just a union of sets. If you know that you're uniformly continuous on S1, S2, Sn, then you're uniformly continuous on their union. But that's kind of like boring unless they overlap, because like, yeah, it's just not as interesting if they don't overlap. It's somehow obviously true. So yeah, using kind of the guaranteeing that they overlap is nice. So if you want to use open intervals, you can. I would just make sure that they overlap in some way. You don't strictly need it, but it's more interesting because we want to be able to actually prove that things are uniformly continuous by saying you're uniformly continuous on this chunk, you're uniformly continuous on this chunk, and therefore you're uniformly continuous on the whole thing, right? So that's why we want this tool. If you remove that so that the two things don't actually overlap or touch, it's still a true result. It's just not as useful to us, right? So that's what I'm saying. If you want to use open intervals, just try and make sure that they overlap just so that the result is still useful. If a delta works, a smaller delta works too, right? Absolutely. Yep, that is always true. And that's why that there are only finitely many intervals here, right? Because you're going to take the min of all the deltas, right? Each interval has its own delta, choose the min, and that delta should work for all of them. There's a little bit of trickiness that you need to check. So for example, when you're looking at what happens if you choose 2 points around the joining point, like the welding point, if you want to consider it that, you run into a little issue in that what happens if one of these points is in I1 and one of these points is in I2. That's obviously not the end of the world to fix, but usually you just have to be a little bit careful there and make sure that you've done things correctly, right? That's basically the only thing that you actually have to do to check this theorem, right? So I basically given you the proof of that, but that'll show up for on your next assignment, because I really like this question. I think it's really, really nice. What if Bn is bigger than An plus 1? Yeah, that should be okay. Yeah, so Cooper, if you want to do the proof there, so what you're actually saying in that case is that the intervals kind of overlap like this, right? And so there's actually a little bit of overlap here. That's okay. Proof should still work. It doesn't change the fact that you kind of have to check the overlap condition still, because you don't know what the delta is. The delta could be bigger than this overlap. So you still have to check it there. But the proof is almost identical, I think. Just off the top of my head, knowing how this proof works and knowing how the proof would work for their overlap, the proof is pretty much the same. So I don't think it makes that much of a difference. So if you wanted to, you could say Bn is greater than or equal to An plus 1 and kind of prove them all at once. And that would be a nice little thing that you could do. Okay. So what I want to do is I'm going to state the theorem that we're going to prove next, but there's no way I'm going to start it because I probably need most of the class to prove this. Okay, so if this function is continuous, then it's uniformly continuous. And it's worth pointing out here that there is a hypothesis here that has not been explicitly stated. So I really want to point that out. So comment. Here it's critical that the domain be the closed bounded interval AB. It is critical that the domain is AB, right? So you notice I didn't write it as a general set D. I didn't say it was an interval I. I'm saying it is closed and it is bounded, okay? It is a closed interval and it doesn't shoot off to infinity. it is both closed and bounded. Those are the two critical conditions that I am going to need, okay? Because otherwise, if you read this theorem, you might miss that. You might be just like, wait a second, are you saying that all continuous functions are uniformly continuous? Certainly not, right? That's not true. Okay, we talked about x squared on 0 to infinity is continuous, but not uniformly continuous. That's not what I'm saying. I'm saying if your domain is a closed and bounded interval, AB, then continuity implies uniform continuity. They are the same, okay? It's not an if and only if, right? 1 over x is an example of a function which is also both continuous and uniformly continuous, but its domain is not closed and bounded. But if I give you a function on a closed and bounded domain that is continuous, then it is also uniformly continuous, okay? This theorem is insanely important to us. Otherwise, I wouldn't prove it for you, because this proof is going to take probably at least 30 to 40 minutes. We're going to take a break. We'll come back. I'm going to prove it for you. But we're going to use this result so many times that it needs to be done. And the worst thing is that I'm going to say to you, we're going to use this result a million times. And you're going to be like, okay. And for the next 6 weeks, you're going to be wondering when I'm going to use it. Because I'm not going to use it at any point in the next 6 weeks, I don't think. Where I'm going to start using it is in January, right? And in January, we're going to use it like crazy. Okay, so quick question, how do we know that the interval AB is bounded? So an interval is bounded, right? Like as a set, it's bounded, right? Because it's bounded above by B, its supremum is actually B, and it's bounded below by A, right? Its infimum is actually A. The only way it could not be bounded as an interval is if it was like A infinity or negative infinity B or negative infinity to infinity, which would just be R. Those are the unbounded intervals, right? So the unbounded intervals have an infinity somewhere inside of them. So we know that it's bounded by default precisely because A and B are not infinite, right? I'm not allowing that to be true, right? Yeah, because continuity implies boundedness. It implies local boundedness, right? But notice I'm not saying that the function is bounded. I'm saying that the interval is bounded, right? I'm saying the interval here is bounded. The function might not be bounded. I actually don't know that that's true. It turns out it will be true. A continuous function on a closed and bounded interval is itself bounded. We're actually going to prove that, if not today, then Thursday. But yeah, we don't know that yet. The open interval AB is bounded, but it's not closed. Yeah, exactly. And Mary says that, right? Okay, so it has to be closed and it has to be bounded and it has to be closed, right? Closed is necessary. I hope I spelled that right. Closed is necessary because if it's not closed, we could do something like this. Right? Because the problem with 1 over x wasn't everything after, it wasn't the stuff that went to infinity, it was the stuff near 0, right? So the closed condition is critical, otherwise we could have things like 1 over x. And the bounded condition is critical, otherwise x squared, right? So both of these conditions is necessary. I feel like there might only be one C, but whatever. Right? So closed and bounded are both needed in order for this theorem to be true, because we have two examples here of if I remove the closed condition and if I remove the bounded condition, it's not true anymore, right? So both of these conditions have to be true in order for this theorem to be true. And we're going to use both of those conditions, okay? Like I said, though, so this proof is going to take a bit, and I don't want to start it. So why don't we take a 10-minute break? So it's about 10:05, basically, by my clock. So let's come back at 10:15. And I suspect this will take a good chunk of the rest of the lecture, but we'll see. And yeah, and then we'll prove it. Okay, so prepare yourself mentally for what is about to hurt. I'll try and explain it the best that I can to make it clear what's happening, but it is long. And just anytime you have long proofs, you tend to get lost in the weeds, right? Okay, so 10 minutes, and I'll meet you back here, and then we'll do the proof of this thing. Zoom. Okay. All right, it's time to prove this theorem. Now, the proof is actually not terrible. It just takes a while because there's a bunch of stupid cases that we have to do. And if you read, for example, Spivak's proof of it, Spivak's proof sweeps a lot of it under the rug, where he says, oh, look, these things are true. This is obviously true. And, I usually don't give Spivak hell because, Spivak is a good book, but like he definitely is short on this proof. And in all fairness, my book is as well. But one day I'm going to go back and fix that in my book. All right, so here's basically the proof of it. Now, this is a proof technique that we're going to use a couple of more times. It's a little bit weird. I call it these forcing proofs. I call it like a forcing argument. The logicians get angry when I call it that because there's actually a technique called forcing in like point set topology, but whatever, to hell with those guys. So, all right, here's what we're going to do. So we're going to define the following function or a set. So define, or let's say fix some epsilon greater than 0. Okay, and we're going to define the following set. So define this set, C sub epsilon. So this is going to be the set of all x in AB such that, let me just double check. I want to make sure that I get this right. Such that there exists a delta greater than 0, such that for every x and y in A, x is a bad choice. For every, let's call it little c. There we go. X minus y is less than delta implies f of x minus f of y is less than epsilon, like that. Okay, that's crazy. So let's take a second to think about this. So I fixed some epsilon. Okay, I'm not doing this for all epsilon right now. I've just fixed one. But what I'm going to do is I'm going to show that the following proof is going to work no matter what epsilon I chose. So let's say I chose epsilon is equal to 1. So what I'm going to do is I'm going to take the collection of all points in the interval AB such that there is some delta which proves that the function is uniformly continuous with that fixed value of epsilon on the interval AC. Okay, does that make sense? It is the collection of all points in the interval AB where my function is uniformly continuous for this value of epsilon. Okay, maybe let me write that down. This is the set of points basically in AB where f is uniformly continuous for this choice of epsilon only. Right? Is that okay? Is everyone bothered by that? So if like epsilon is equal to 1, I'm saying C epsilon is the points in the interval AB where I am uniformly continuous with epsilon equals 1, right? And then when I'm going to let epsilon be a half and do the same sort of thing. So what we're going to show, so one, we're going to show that the supremum of C epsilon is B, i.e. it's, the function is epsilon uniformly continuous for the entire interval AB, right? So i.e. f is uniformly continuous for this epsilon on the whole interval. And 2, this doesn't depend on epsilon. Okay, and if I do that, I'm done. Because then I will have shown that I satisfy the definition of uniform continuity with this version of epsilon on the entire interval AB for any epsilon, right? And that is the definition of being uniformly continuous. So this is what I'm going to do. This is our goal. So step 1, show that the supremum is equal to B. Step 2, show it doesn't depend on epsilon. We're actually kind of doing step 2 already because I said fix some epsilon greater than 0, and we're going to show now if I show step 1, I've implicitly done step 2 at the same time. Okay, so let's show that the supremum of C epsilon is equal to B. So if for a supremum to exist, we need that the set is non-empty and bounded from above, right? The set is certainly non-empty. Now, why is it non-empty? Because A is in the set, right? Right. So the singleton A, the function is continuous at A, therefore it's uniformly continuous on the interval A to A, right? It's kind of dumb, but yeah, it does work. A is in C epsilon. It's quote unquote uniformly continuous at the singleton because it's continuous there, i.e. there is one delta, which works. So A is in here and B is an upper bound. For C epsilon, right? Why? Because we said by definition, C epsilon is the set of all points in the interval AB. So yeah, the biggest that anything in C epsilon could be is B, right? What is the C after the for all X and Y in AC mean? So this C and this C are the same, right? So basically what we're doing is we're trying to find the biggest interval on which the function is epsilon uniformly continuous. And what I'm going to do is by saying, let this set be the collection of all points where it's epsilon uniformly continuous. And I'm going to show that's actually the whole interval. That's what I'm doing. Right. So it's sort of like, let's say I'm doing this on the interval 0, 1. Right. So sort of what I'm doing is I'm saying, okay, look, is it uniformly continuous on this interval? Yeah. Okay. Can I go a little bit further? Oh, yeah, it is. Can I go further? And so then I want to kind of like, this is what I mean by it's like a forcing argument. Like I'm just trying to push that all the way to the edge, right? Cool. Okay. So A is in there. It's because, again, if you're continuous at a single point, then there is a single delta, which works. It's bounded from above. So by the completeness axiom, the supremum exists. So by the completeness axiom, I'm going to call it maybe S sub epsilon is the supremum C epsilon exists. Okay, capital S for supremum. And then I'm going to call it S sub epsilon just to remind us that this actually depends on epsilon, right? If I choose a different value of epsilon, I'm going to get a different S sub epsilon. Okay, so claim S sub epsilon is equal to B, right? So this is me proving number 1 there. I want to show that the supremum of C epsilon is equal to B. So claim S sub epsilon is equal to B. All right, so the proof of this claim, well, certainly S sub epsilon is less than or equal to B, right? Since B is an upper bound and S sub epsilon is the least of the upper bounds. So since B is an upper bound, so let's assume that it's strictly less than for the sake of a contradiction. So for a contradiction, suppose it's strict. Okay, strictly less than B. Okay. Whew. So this means that S epsilon is in the interval AB, right? And so f is continuous at s sub epsilon. Not uniformly continuous, just continuous. Okay, so therefore, choose a delta. I'm going to call it delta sub c for continuity, such that if x minus s sub epsilon is less than delta sub c, then f of x minus f of s sub epsilon is less than epsilon over 2. Okay, and you'll see why epsilon over 2 later. Again, if you're doing this proof, you would just say epsilon for now and you'd fix it later, right? Okay, so here I'm just using continuity. I'm not using anything about uniform continuity. I've assumed s sub epsilon is strictly less than b, so it's strictly inside of the interval ab, and therefore we assumed by assumption that my function was continuous, so I'm continuous there. So this is me just invoking the definition of continuity of the function at the point s sub epsilon, all right? Okay, so let delta be a delta, well, let's say let delta, let delta be a delta? That's a weird statement. Let delta be the number which works for C epsilon. So remember, by the definition of C epsilon, there exists a delta. We don't know what that delta is, but we know it exists. So let's pick one. And then let's set delta hat to be the min of delta C divided by 2 and delta, right? Okay. And now at this point, you're like, why did you do all that? You'll see in a second. So basically what I want to do, let me kind of sketch out a picture here for you. So you have an idea of what's going on. So here's S sub epsilon, right? So what I want to say is, well, I know that my function is basically uniformly continuous with this choice of epsilon on this set, right? There's basically this set here is C epsilon. Technically, we don't know that it's a full interval, but whatever. Let's pretend that it is, just for the sake of our intuition. So C sub epsilon is this whole interval. Actually, we do know it's a whole interval. Yeah, never mind. So C sub epsilon is this whole interval. We know that we're uniformly continuous on this interval. But I also know that I'm just continuous at S sub epsilon. So I get this, delta C, which works on either side of S sub epsilon. So what I'm going to do now is say, well, look, if I use this delta hat, then I can actually extend the definition of uniform continuity so that it includes all the way up to S sub epsilon plus delta hat. And that's going to give me a contradiction, right? So I'm going to use continuity at S sub epsilon to push uniform continuity. This is what I mean by it's kind of like a forcing argument, right? I'm going to force uniform continuity to actually extend further than S sub epsilon. And that's going to contradict the fact that S sub epsilon was the least upper bound of C sub epsilon, right? Because now I've actually extended uniform continuity a little bit further. Does that make sense? So I'm going to use continuity at S sub epsilon to push the uniform continuity to make it a little bit bigger. And that contradicts the fact that we're already as big as we can be, right? Okay, so how do we do this? Well, we have to do now cases, because the cases are basically going to be, am I in the blue interval or am I in the red interval? So I'm going to choose 2 points, which are a distance delta hat apart. And I'm going to say, listen, you're either both in the blue interval, you're both in the red interval, or one of you is in the blue interval and one of you is in the red interval that doesn't include the blue interval, right? We do this until, well, basically I've already assumed, like I don't need to keep pushing it. The picture is a little bit weird because I'm already in contradiction land, right? I've assumed that S sub epsilon is less than beta, and that actually isn't possible. We're going to prove that it's actually equal to, or is less than B. I'm actually going to prove that S sub epsilon is equal to B. So it's not even that I'm constructing the proof directly by continuing to force it until I get to B. I'm saying that if I assume that it's strictly less than, I get a contradiction because I can force it to be bigger, right? It's like, assume that there's a biggest natural number. Well, I can actually force there to be a bigger natural number by adding 1 to it, right? So that's basically what I'm saying, right? Assume there's a biggest natural number. I can force there to be a bigger natural number. That's a contradiction. So assume that S sub epsilon is strictly bigger than B. I can actually use continuity to force uniform continuity to be a little bit bigger, and that's gonna be my contradiction. Where does delta C over 2 come from? You'll see in a second. Basically, the delta C over 2 comes from the fact that if I choose a number here and I choose a number here, those things are further than delta C apart, right? Because this is delta C. This is the distance delta C here. Or rather, if I use delta C, that would be delta C. So if you choose two things on the furthest ends of your delta C band, then they're actually more than delta C apart, because we measure distances from S sub epsilon, not from any 2 points in the delta C band. So if I chose any 2 points in the delta C band, they could actually be really far apart, relatively speaking. So by using delta C over 2, I can actually guarantee that things are, right? Like maybe this is the delta C band. So by using a half, I can guarantee that any 2 points are within delta C of each other. Yeah. Does that make sense, Jay? Like why I'm using that? Is that okay, or did you actually get it? Right? Because I feel like okay is not I got it. So if I say if I say here just as a side thing, x minus c is less than rho, what does that mean? So here's c plus rho, here's c minus rho. And so I'm saying the distance of any point, okay, but so here, let me explain it. So I'm saying the distance from any point to C is at most rho. But what is the distance between these 2 points? It's actually bigger than rho, right? So what I'm going to do is, if I still want to guarantee that 2 points are within rho of each other, I'm going to use rho over 2 on either side of C. And now those 2 points will always be within rho of each other. That's the idea. That's where delta C over 2 comes. We want them to be at most delta C because I need to be able to use this. You'll see. So the definition of uniform continuity says if the absolute value of x minus y is less than whatever my delta is, then f of x minus f of y is less than epsilon, right? So if I want to be able to use this definition of uniform continuity, I might need to be tricky about my over 2s, right? But maybe I don't need the over 2. Let's try it. Let's see what happens. Okay, so case 1. So now what we're going to do is we're going to say, suppose that the absolute value of x minus y is less than delta hat, right? And delta hat is this thing here right before I drew the picture, delta c divided by 2 or the min of delta c over 2 and delta. Okay, so case 1. So if x and y are both in a s sub x, then the fact that x minus y is less than delta hat, but delta hat is less than or equal to delta, implies that f of x minus f of y is less than epsilon. Everyone agree? Basically, this is if the x and y are both in the blue thing, then, or sorry, s sub epsilon, right? So I've said if x and y are both in the blue thing, well, the fact that they're both less than delta hat and delta hat is less than delta automatically gives me f of x minus f of y is less than epsilon, right? Because that's what the blue hat stuff does. Okay, so case 2. So let's suppose that x is in a S epsilon, and y is in S sub epsilon. What do I want? Let's use open interval minus delta S. Okay, so X is in the blue and Y is in the red. Okay, so if this is true, then X minus S sub X is X. Well, let me just go straight to less than. Is that what yes. Okay, so X minus Y, that's going to be less than delta hat. And then Y minus X sub S is also less than delta hat. So that's less than or equal to delta C over 2 plus delta C over 2 equals delta C. Thus, fx minus f of y is less than or equal to f of x fsx plus fsx minus fy is less than epsilon over 2 plus epsilon over 2 equals epsilon. Okay, so do you see why the delta C over 2 ended up becoming useful here? Because I wanted to guarantee that x minus s sub x, or x was within delta C of s sub x, so that I could use that here. Again, this is me using continuity of f in order to expand the C sub epsilon interval, right? Does that make sense? Everyone okay with that? Oh, I keep writing s sub x, sorry, s sub epsilon. If I write it, it's s sub epsilon. Okay, everyone's good? Right, so again, the idea here, you've got s sub epsilon, you've got this delta hat distance in either direction, and then you've got, what do you want? So we've got like x here, we've got y here, and I want to show that that f of x minus f of y is less than epsilon. So I'm going to use the fact that x minus y are sufficiently close to each other and sufficiently close to s sub epsilon in order to guarantee that I get what I want, right? There are more s sub x's that need to be changed. Where? Oh, there's one. I see. Yeah, there are two here. Thank you. Yeah, in my notes yesterday when I was writing this up, I was using s sub x, and now I've changed notation, so that's why I'm screwing up. Y, yeah, thank you. Anyway, you know s sub x is going to be s sub epsilon, right? If I write that. Just forever now after, those two are the same thing. Right? Because yeah, in my notation, in my write-up of this from yesterday, I use s sub x. I don't think anyone could probably see them, but they're there. Okay. And now finally, case 3. So if both of them are within the delta hat band, then great. So if x and y are both in s epsilon minus delta hat, s epsilon plus delta hat, then we're done. I don't even think I need to do anything. Oh, I guess I should say this. Then the distance from x to y is less than or equal to the distance from x to s sub epsilon plus y to s sub epsilon. Is that what I want? Yes. Is less than or equal to delta hat plus delta hat. That's going to be less than or equal to delta c over 2 plus delta c over 2 is equal to delta c. So f of x minus f of y less than or equal to f of x. Same sort of thing, right? Minus f of s sub epsilon plus f of y minus f sub epsilon less than epsilon over 2 plus epsilon over 2 equals epsilon, like that. Okay, so what I've shown now is that delta hat satisfies the epsilon continuity for 0 to s epsilon plus delta c. Thus, delta hat shows this epsilon uniform continuity for or on a s epsilon plus delta hat. And this contradicts the fact that s epsilon was the least upper bound. Actually, it just contradicts the fact that it's an upper bound. Okay, so does that kind of make sense? I know there's a lot going on there, but basically we said A to S epsilon is the biggest set on which we get the epsilon uniform continuity. And then I use the continuity of the function at S sub epsilon and a slightly smaller delta hat, but that's fine because if you have a smaller delta, if you use a smaller delta, that's fine. I've shown that there exists this smaller delta, which actually extends and pushes the uniform continuity a little bit further. And that contradicts the fact that S sub epsilon was an upper bound for this set. Okay. And then, so the only thing that is left, so thus S sub epsilon equals B, which notably does not depend on epsilon. And so now you have to just convince yourself that S sub epsilon is actually in C sub epsilon or C of epsilon. So convince yourself. I'm going to leave that part for you because there isn't anything to do. That B is in C epsilon. So it's not just the supremum, but it's actually in the set. And thus we're done. Okay. And so we've now proven that the function is uniformly continuous. Oh man, if I try to zoom out for the whole proof, it's a little bit small. Okay, so like I said, this is a long proof. This proof actually isn't like it requires this trick. And this is a trick that, like I said, we're going to use a couple of more times, but it does use this trick. But like once you have that trick down, the rest of the proof isn't too bad if you can kind of see what's trying to happen, what the movie is. It's again, it's this forcing argument. If it's not everything, then I can force it a little bit further ahead. Okay, I guess I should say, actually, I did use something implicitly. Here, I did use that exercise above. Right? That if you're uniformly continuous, actually, no, I don't think I did. If you're uniformly continuous on one interval and you're uniformly continuous on an interval adjacent to it, then you're uniformly continuous on the whole thing. I actually don't think I used that result because I just used delta hat to prove it for the whole thing. But in any case, that's how you prove this thing. It turns out in 257, we proved this result again, and it's much easier. Believe it or not, the second year proof of this theorem is much easier than the first year proof of this theorem. That will also be true of the next two theorems that we prove, which are also have nasty, nasty proofs. Okay, so are there any questions about this? I bet there are, just people are too afraid. Okay. So this actually really, this is very, very powerful. And the reason for this is, I mentioned above that the square root function is uniformly continuous on 0 to infinity, right? In fact, closed 0 to infinity. So if you wanted to prove this, don't try and prove this from scratch. The actual way that you would prove that the square root function is uniformly continuous on closed 0 to infinity is to do the following. Basically, the square root function is uniformly continuous on the closed 0, 1 by this theorem. Then prove that it's uniformly continuous on 1 to infinity. That turns out to be better because 0 is a tricky point with the square root function. But then you show it's uniformly continuous on the interval 1 to infinity, and then argue that you can just choose the smaller of those two deltas. Very similar to this argument that I referenced above, where if you're uniformly continuous on adjacent intervals, that you can combine the uniform continuity. It's the same sort of argument. Okay, so this is great. And like I said, this is going to come up a lot when we do integration, because when we do integration, we're always going to have a function on a closed and bounded interval. And so we're going to have that it's uniformly continuous, and all of the proofs in integration are going to use uniform continuity. So it's going to be super, super useful for us when we get to integrals. Okay, but you might be like, oh, yeah, you said it was going to be useful, and then we didn't use it till January. Okay, but I've warned you about that now ahead of time. Let me set up, it does not depend on epsilon because we fixed some epsilon in the beginning, right? And then the answer was just always B, regardless of which epsilon I chose, right? So epsilon had no impact whatsoever on the fact that it was B, right? That its supremum was B. So it must hold for all epsilon. And if it holds for all epsilon, that's what I need in order to get uniform continuity, right? Okay, so I'm going to state the next two theorems just so you know that what we're going to. I don't think I'm going to try and prove them just because it's going to take a second. So here's what we're going for. And I'm always curious whether people know these theorems or not, because I can't remember whether they're talked about in high school. Okay, so here's the theorem statement. No, I guess I usually consistently yellow. If f from AB to R is continuous, f of A, let's say, is strictly less than f of B. Of course, you can flip them around as well, right? Okay, you've heard about it? All right. I kind of want to say and f of A is less than B. I just want to fix my English a little bit here. Then for every D in FA, FB, there exists some C in AB such that f of C is D. Okay. So this theorem says continuous functions can't jump. Right? This theorem says if I graph a function, and let's say I take the function like this. So here's f of A right here. Here's, let's say, f of B. Okay. So the theorem says for any number between f of a and f of b, there's some point on the curve which achieves that, right? So if I say, yeah, let's let this be d, be this height, and I walk across, there's some number c between a and b, such that f of c is equal to d, right? And again, like there's some sense in which this is obvious. You know that the function is continuous on the entire interval, so it can't jump over any numbers, right? That's not possible. So the theorem says that for any number between f of a and f of b, there's some, like the function has to hit every number between f of a and f of b, right? So you know the function starts at f of a, you know it ends at f of b. And yeah, there are actually some points outside of this interval as well, but the theorem doesn't tell us anything about those. It just says the function has to hit every single number between f of a and f of b. And it's continuous, so of course it has to. Does everyone agree? Like there's some sense in which this is an intuitive function. If I tell you to draw a function that starts at f of a, that height, ends at f of b, and is continuous, so you can't lift your pen from the page, well, there's no way you can draw that doesn't include every number between values, because then it wouldn't be continuous. Okay, and then there's the extreme value theorem. And it says if f maps AB to R is continuous, then there exist M and M. Maybe let me make that more clear. One of those is lowercase, one of those is uppercase. Such that for all x in AB, okay. So if C is inside AB, then f of C is inside f of AB. I mean, no, you know that. So you know that is true for sure. Oh, that's actually, yeah, no, that's actually not true, right? So notice that C, this value here is in the interval, but its function value is actually outside of f of A, f of B, right? So it's not what the theorem is telling you. The theorem is telling you that if you start with a number on the, say, the y-axis, oops, didn't mean to delete that. So it says if you start with a number d on the y-axis, then you can find a number on the x-axis which maps to it, right? But you don't know that if C is in AB, then f of C is in f of A, f of B. Yeah, you don't know that because it could go actually above and then come back down, like I've drawn here. Okay, so the extreme value theorems, but what happens with the constant function? I mean, so in that case, the theorem technically doesn't apply, or it technically does, depending on you want, because the theorem says that f of A has to be less than f of B, and a constant function doesn't satisfy that. But it's, you could argue that it's just less interesting because there's only one number between f of A and f of B if they're the same number. And yeah, every number in the domain, like every point in the domain gives you that value of the function, right? So is this saying that every bounded continuous function has a minima and maxima? So notice it doesn't say anything about bounded. It doesn't say that the function is bounded at all. In fact, the fact that the function is bounded is part of the theorem, right? So it says that if I give you a continuous function, yes, okay, define it on a closed and bounded interval, right? So a continuous function on a closed and bounded interval is one, itself bounded, and two, achieves its maximum and minimum. Right? That the minimum is f little m and the maximum is f big M. Right? Because these aren't just bounds. We're not just saying that f of x is always between some number and some other number. We're saying there are actual values of f which make the function a minimum, right? So comment, so this is the min, this is the max, hence the big and small letters. So comment 1, this shows f is bounded. Is bounded. And 2, this shows f achieves its max and min. Okay. Is this the same reasoning we talked about in the last theorem? Which reasoning? So if you can point to that specifically. And here, let me show you the importance that this function, that it has to be a closed interval as well. Okay, bounded is not being enough. The thinking is, it depends again on what you mean by the thinking. No, I'd say the thinking here is a little different, because here I'm not saying that it has to hit every number between its max and min. What I'm saying is that it actually achieves its maximum and minimum. So first of all, the function is bounded and it achieves its max and min. So let me show you. Let's do some examples. Here's this function. Okay, this is a really easy function, right? It's just the identity function. Does this function achieve its maximum? What is the supremum of this function? It's 1. Is there any point where it achieves the number 1? No, right? Exactly, we can't find it because it's not closed. So here the function is bounded, but there is no number capital M in the interval 0, 1 such that that 1 is actually achieved, right? Do we see this, right? Like the maximum here is not actually achieved. This function does not have a maximum, right? There's no value in the interval 0, 1, which is bigger than every other value in 0, 1, right? Because the function is monotone increasing. So if you try and tell me that 0.99999 is the biggest number, I'll just tack on another 9 to that and I'll get a bigger number, right? So the maximum, this function does not have a max. Right? It has a supremum, but there is no maximum to this function. Is everyone okay with that? You see the difference, right? The maximum actually has to be achieved. The supremum does not, because the supremum doesn't have to be in the set, right? But the maximum does. The maximum actually has to be in the set. Is everyone okay with that? But the moment I close off 0, 1 and I actually include the boundaries, then the theorem above, the extreme value theorem, says, no, actually you can find numbers such that the minimum is achieved, right? There's actually a value in the interval of your domain where the maximum and minimum are actually achieved, right? You don't just get arbitrarily close to the max, you actually hit the max. And that's what the extreme value theorem is telling you. You don't just get arbitrarily close, you actually get it. Okay? Does that make sense? And so here it's a little bit harder to see the intuition, and actually this proof is much tougher as a result. But it's a little bit harder to see the intuition for why it's continuity on the closed and bounded interval that would give it to you. I mean, in some sense, it's clear why it has to be closed and bounded. Here's an example of why it has to be closed, because otherwise your supremum can be achieved at a boundary point and you don't actually achieve it. And of course, if you're not bounded, well, then there are no boundary points. If I took this to be the interval closed 0 to infinity, the function wouldn't have a maximum, right? Because it keeps getting bigger. So the fact the interval has to be closed and bounded, but then, well, why does it have to be continuous? Well, it has to be continuous. Otherwise, you can do on a closed and bounded interval, you can do like a vertical asymptote, right? And then the function doesn't have a maximum again, because you have maybe a vertical and or a vertical asymptote that goes towards both positive and negative infinity. And that tells you your function gets arbitrarily large and arbitrarily negative. So continuity guarantees that you're bounded. And then the closed and boundedness of the interval, it guarantees that the maximum is actually achieved, right? So does that make sense? Is everyone okay with that? Okay, I'm going to assume close enough. Maybe just spend some time thinking about them and think about how you might even use them. And we're going to prove them on Thursday. All right, so there's some stuff to do here. The intermediate value theorem is actually pretty quick, but the extreme value theorem is a little bit longer. It takes a little bit of extra work. But again, we're going to use both of them. They're both going to be super important, and they're going to come up a lot, not only this year, but next, in upper level years as well, especially if you go take something like 257. Okay. Yeah. Hey, I was arguing. I think there should be an extra reading week, in a couple of weeks, but I mean, can't convince anyone to do that. If f of c is in f of AB, then the preimage of f of c is inside AB. Yes, that's true. But note that, yeah, f of AB is, so just as kind of like an aside, and of course we're done today. So if people need to leave, of course you can. So note that this is not the same thing as this, right? Those can be very different. And generally, if f is continuous, you can guarantee a subset relation. So the left is a subset of the right. That's actually what the intermediate value theorem says. So yeah, actually, if f is continuous, then this is true. This is the IVT. But if f is not continuous, you can't even guarantee that, right? So the guarantee, the intermediate value theorem can be thought of as guaranteeing to you that you can put a subset here, which is maybe a nice way of thinking about it. Okay. All right, everyone. So that takes care of our lecture for today. I want you to think about these two theorems. Even better, see if you can prove them. Again, these proofs are tough, though. These proofs are actually really hard. But if you want to take a crack at them, maybe throw it on Piazza, and I'll try and give you a hint there. Otherwise, though, I'll take these up on Thursday, and we'll deal with them then. Okay. All right, everyone. So I can't hang out too long. I think I actually have a meeting. So I have to run. But it was good seeing you, and I will see you on Thursday morning. Thanks, everyone. Yeah, see you later.